So here it is. You may remember, or you may have heard, that Einstein's relativity,
Right.
more specifically, you learn this in special theory of relativity, where the faster you move,
Right.
the slower time ticks for you
Right.
as others view it.
Relative
okay?
to the observer.
Relative to the observer, correct. You don't know anything's happening.
Right.
Your clock still ticks as far, you still got your heartbeat, all of this. Okay, so this is not a physiological thing. It is an actual property of the fabric of space and time under those conditions.
Wow.
Okay?
That is fascinating.
It is. It's completely fascinating. It's completely. So I watch you fly by, and the faster you go, the slower time ticks for you. Okay?
But my time stays the same.
To you.
To me. Right.
To you. So not only does speed do this, also the strength of a gravitational field will have the same effect on you. The stronger the gravitational field is, the slower time ticks for you. And that wasn't formulated until his general theory of relativity 10 years later. That took a lot more math and deeper insights into the universe. The title of the research paper was On the Electrodynamics of Moving Bodies.
What?
Okay, that was the title. We would later call it the special theory of relativity because it was a special case of what would later then be called the general theory of relativity. While we're there, let me just slip this in. The GPS satellites orbit higher than like the space station and other things that are in what we call low Earth orbit.
Low Earth orbit.
They're in like MEO, middle Earth orbit. There's LEO, MEO, and GEO. The geosynchronous satellites are like middle orbit. That is far enough away from Earth's source of gravity for them to have a measurably different space-time condition.
Oh.
So that their clocks tick faster than our clocks on Earth's surface because they're farther away. And so remember I said the more intense the gravitational field is, the slower time ticks. So they're farther away. Their time ticks faster relative to us.
Wow.
But we get precise timings from geosynchronous satellites. So how does this work? We pre-correct the time signal from the GPS satellites to compensate for Einstein's general theory of relativity so that by the time the time reaches us, it's been properly corrected and it matters to us and our space-time continuum, not the one that's in middle Earth orbit.
Oh my goodness.
So GPS couldn't work as accurately as it does.
However, wait a minute.
What?
I'm sorry, just for me. You would have to have a standard in order to pre-correct something.
You know the rate at which its time is speeding up because you can calculate what the gravitational field is up there.
There you go. Okay.
And once you calculate that, then you do and you say, oh my gosh, the formula works. Einstein was right.
Right.
All right. This is not just something on a high theory, hypothesized that may or may not be true. It is true.
I just want to be there when that phrase is uttered. Oh my God, Einstein was right.
Yeah, these aren't just cult heroes that we wish they were right. These are real. This is real. Okay, this is the real universe we're talking about here. Okay, so now watch. Let's keep going faster and faster. Okay. Let's go half the speed of light, three-quarters the speed, 90% the speed of light, 99% the speed of light. Mm-hmm. Time is ticking slower and slower and slower. For you, you will watch the whole future history of the universe unfold in front of your eyes as fractions of a second go by for you. As you go 99, there's a formula for this, of course, but 99, 99.9, 99.99% the speed of light.
Because you're the observer of that. But for you, your time has slowed to the point where as you observe the things that are not moving at the speed of light, you see them
speeding.
Basically,
correct.
You see them unfold.
Correct.
Boom. God.
Correct. Some particles. Let's take, for example, the proton or the muon. One of these decays in like 6 minutes when it's left out in the wild. okay, when it's not part of an atom.
Okay.
When it's not in captivity, I forgot which of these, but it doesn't matter for my example. Decay isn't like 6 minutes, okay? Okay. What happens if you take that particle and speed it up in a particle accelerator? So you take a community of these particles, speed them up, calculate, wait a minute, the internal wristwatch on these clocks says they should live longer. And sure enough, their decay time takes longer.
Wow. That's, oh my God.
Yes. Yes.
So oh, wow.
Yes.
And that becomes living proof of what Einstein said.
Yes, because we can't go half the speed of light.
Right.
But you can accelerate a particle to do that.
Yes.
And it has an internal built-in clock that decays after a certain amount of time. And there they are taking longer to decay in the exact amount that Einstein predicts.
That is genius.
So we don't make this stuff up, okay?
Yeah.
Yes, it is genius. It's like triple genius. All right. Now, let's take this to an extreme level.
Right.
Let's go so fast that we're going the speed of light itself.
Right.
Well, we can't do that because we're made of material substance, and there's no way to do that. But there are things that travel at the speed of light. And what is that?
Those would be photons.
Yes. Thank you. I like those would be, I like your finger gesture. That would be, I would say, what travels at the speed of light? Light does.
Yeah.
Okay.
I was about to say light.
So if photons had a clock, the clock would never tick.
Nice.
Which means when I go to a mountaintop, as I did in graduate school, to observe the center of the Milky Way galaxy for stars that emitted their light 30,000 years ago, traveling through the gaps of interstellar space, and they move through space, come through Earth's atmosphere, they come down into the telescope, they reflect, go back to my detector, and land on my CCD chip. That photon, when it was born, at the star that emitted it, was detected at my telescope in the same instant.
Wow.
According to the photon itself.
Live fast, die hard.
The photon has no knowledge of that trip.
Right.
Because time did not exist for it.